Okay, into our next video on magnetic fields, and hopefully there will only be two for this subtopic. In this video we're looking at an example problem from the theory we just talked about at working out the force experienced by a current carrying wire in a magnetic field, and then finally we will talk about the application for this topic, which is how speakers work, and which is quite a neat one. Okay, so we've got a previous exam question here that looks at magnetic fields. So in the first part, the diagram below shows a straight conductor carrying a current perpendicularly out of the page. So we've got this little arrowhead for perpendicularly out of the page. Draw the direction of the magnetic field. So I'm going to point my thumb out of the page, make sure I've got my right hand, my fingers follow the curl. So hopefully it's going to go like that. So obviously at this point A, the direction of the field would be like that. The tangent to the line at the point A would point directly to the left. Okay, part B. The straight conductor carries a current of 2.5 times 10 to the minus 3 amps. The conductor is now placed in a uniform magnetic field. B equals 0.30 Teslas. Sorry, Teslas is what the unit we use for magnetic strength. I think it was mentioned on the slide, but I didn't really talk about it earlier. Directed to the right, as shown in the diagram below. Determine the magnetic force acting on a 0.15 metre length of conductor. Now, I reckon these are pretty simple problems, so I hope you can see this is pretty straightforward. So, what's the information in the question? Well, it's telling us that the current is equal to 2.5 times 10 to the minus 3. The magnetic field strength is equal to 0.30 Tesla. The length is equal to 0.15 metres. And we can see here that the current is out of the page. The magnetic field is in the plane of the page, so the angle between those two is equal to 90 degrees. What's our formula say? Step 2, force equals, I forget what it says on the formula sheet, but I always remember it as Bil, B-I-L, times sine theta. So that's equal to 0.30 times 2.5 times 10 to the minus 3 times 0.15, that's in metres, so that's all good, times the sine of 90, and that should be equal to, let me pause and get my calculator. Okay, so we've got 1.1 times 10 to the minus 4 newtons. And then in part C, the orientation of the conductor is now changed so that the direction of the current is to the right. So instead of out of the page, we can imagine now the current is to the right, going in the same direction as our magnetic field. Explain how the magnetic force acting on the conductor would change. So there's two clear things we want to demonstrate here. First, we want to show that the magnetic force would now equal 0. So magnetic force would equal 0. But now we need to explain that. So I'll change back to green. We just need to we could talk about the fact that sine 0 equals 0, therefore the force equals 0. We could use the formula, so something along the lines of, theta equals 0, therefore sine theta equals 0, therefore force equals 0. Or the alternative way is we could just talk about the fact that there is no force if current is parallel to field. Okay, so unfortunately these sort of questions aren't in the exam all that often, which is a pity because I actually think they're some of the easier questions normally on the magnetic field stuff, but hopefully this year there will be one there and hopefully you will do very well at it. Cheers. So let's finish off this topic by talking about how a speaker, or in this case a moving coil loudspeaker, but that's the most common type of speaker, works. So firstly we're going to describe the components. So the components of a speaker are a cone, or sometimes called a diaphragm, often made of like a paper material. That actually is the part that vibrates. When that vibrates, it makes the air particles vibrate. And basically sound waves are basically vibrations of air particles. So that basically creates the vibrations in the air. That is hooked up to a moving, a voice coil, or a moving coil, which is basically, if you like, a temporary magnet. So it's a solenoid, so when you pass a current through it, creates a magnetic field, which is then going to react with, or interact with, better than react, the field from a permanent magnet. So that is, if you like, the magnet structure that it's talking about there. And then we have basically this supporting frame in both cases. Here we talk about the basket. Here we talk about the supporting chassis, which holds this in all together. So how does this sound wave, if you like, these vibrating air particles get created? So firstly, we can imagine that we have a permanent magnetic field, and that permanent magnetic field is in the direction that the north pole of the magnet will point to. So the permanent magnetic field is going up here like this. So then, in the coil, we have the current going through that wire, which is in the magnetic field. So let's say if at the top it was going into the page, we could use our right-hand palm rule. Our fingers are going to point straight up. Our thumb's going to point into the page. So in this case, our palm is pointing forward, so that that voice coil and the attached cone, so the voice coil and the attached cone, is going to get pushed up. Let's just double check at the bottom. If it's going out, if it's going into the page at the bottom, it's coming out at the top. So in that case, the magnetic fingers point downwards, the thumb points back at you out of the page. You can see the force is coming out of the page. If we flick to a different colour, now if this then gets flipped, and we do this by just alternating, having an alternating current, so flick the positive and negative on the circuit, we'll see now at the top, fingers point up, thumb points out of the page, palm points back here to the left. So that would make it vibrate out, back inwards. At the bottom, we'll just double check we get the same thing. Fingers point down, thumb points into the page. I always love when people are doing these questions in a test, watching all the sort of hand gymnastics that they do. We can see that when that current is reversed, that pushes in. So as you keep alternating this current, positive, negative, positive, negative, positive, negative, that'll make the speaker vibrate at the same rate, and then that'll create sound waves with the same frequency as the alternating current here. And by varying that alternating current, you vary the frequencies or the pitches of the sounds to create all the different sounds that we know and love to listen to on our speakers. Very common question. This question, how does the speaker work? Going through that process, just like I've done there in the coloured type with the different colours. Much more common than probably the mathematical problem-solving type question that I just went through. So, make sure you have a really good understanding of how a speaker works And yeah, that is it for the magnetic fields topic. Thank you.